Hello, welcome to our seventh and last session of Python Foundations. Today, we will be going over the package Numpy. As I've said before, feel free to check out the previous sessions if you haven't done so already. You can find them in the YouTube playlist for this course series. You can also find each video link at the top of the notebooks in the Python Foundations website. We will begin Python Foundation Session 7, Numpy. Numpy is short for Numerical Python and contains tools for efficient manipulation of arrays of data. If you have used other computational tools like IDL or MatLab, Numpy should feel very familiar. So we'll use this standard alias with Numpy, that is NP. So we'll import Numpy as NP. Numpy has a suite of random number generating tools associated with it. We can seed those random number generating tools like so, calling np.random.seed and setting this to some value. You'll see a lot of other folks do this. The seed value of choice, for those in the know, is the number 42. All right, starting with creating NumPy arrays. When we worked with lists, we saw that we could fill them with all sorts of data types, right? I think the example we used was elephants in the zoo eat pie or something like this, right? And we had integer, a floating point, string values. NumPy arrays are necessarily of one data type. And this has to do with the way they are stored in memory. A lot of the computational speedup that we get from NumPy is predicated on the fact that everything in the array object is the same data type. So in this list of 1, 2, 3, 6, 5, and 4, all of those are going to be integers. And then in this list with 1, 2, 6, 5, 4, and 3.14, those are all going to be floats. We can check the data types in the standard way. Here's my array that I'm creating. I'm just going to loop through each one and look at the type of that element. We see that for this list, everything is an integer. We see that all types are upcast, okay, to the most complex object in the array. For instance, because 3.14 is a float, all the other numbers in the array will be a float. Right? So here we've got float 64 instead of integer because of that one value in the array that had to be interpreted as a floating point. We can also specify the data types in the array by passing a value to the dtype parameter. Right, so here I'm specifying that I want them to be float 32 rather than float 64. Exercise 1, specify data type. Create an array of 5 numbers whose data types are 16-bit integers. Make one of the numbers not a whole number. What happens to the number when it is stored in the 16-bit integer array? Again, if this is your first time here, feel free to pause the video if you would like to work on the exercise yourself. I am going to go ahead and work on it. All right, so an array of 5 numbers. So I'm going to call np.array. And then data types are 16-bit integers. So I don't think it matters. Make one of the numbers not a whole number. So we'll do 1, 2, 3, 4, and then 5.6. dtype equal to int 16. What happens when it is stored in the 16-bit integer array? We see that 5.6 was floored at the value of 5, right? So we just cut the decimal off. No rounding there. It's just removing the decimal. Interesting behavior to be aware of. All right, creating arrays from NumPy methods. Create an array of 10 zeros. How can we specify the data type? Check it out. So this method np.zeros, the first parameter we pass to it is just the number of zeros we would like, and it creates an array of zeros. We specify the data type. Yeah, check it out. I can pull up my tooltip. It says there's a dtype flag here. Let me put in int, see if that works. Looks like these are all integers, right? Your decimal is not there anymore. We can also create arrays of ones. So here I'm just calling the method np.ones. Awesome. We can also fill an array of some arbitrary value and some arbitrary shapes. So we do this using the method numpy.full. The first parameter that I'm going to pass is going to be the shape, And the second parameter is going to be the value that I want to fill that array with. So 642s, all right? We can change this to an arbitrary number of dimensions. So now I've got 3 dimensions. We could also just keep it at 1 dimension. Amaze sauce. All right, arrange from start inclusive to stop exclusive integers with a step size. What does this remind us of? If you're thinking range, that's what I'm thinking tool. 2. So numpy.arrange, very similar API to the range function in vanilla Python. We have a start, a stop, and a step. The stop is exclusive. The start is inclusive. We can verify this concretely by changing the step size to 1. Excellent. Create an array of numbers that divides the space between start and stop, inclusive, with x equally spaced intervals. All right, this is going to be numpy.linspace will be the method we employ here. All right, so we'll start at 0, stop at 10, inclusive this time, inclusive upper bound. Right, this is not the normal, what we normally expect, so it's good to note when it happens. And so we create 5 number values here, right? So and each of one of these are equidistant from its neighbors. np.linspace, super useful function here to be aware of. Create an array of values drawn from a uniform distribution. All right, so this is going to be under the random module in the NumPy package. So we're going to go np.random, and the actual function that we're going to call here is the random function. It's going to produce a number between 0 and 1, all with equal likelihood. We can do this for 5 numbers, 10 numbers, right? This parameter is going to allow us to specify how many random numbers we would like to have. Another important function in the random module, create an array of values from a normal distribution. All right, so again, random module, the function is going to be called normal. And then we have the center point under the parameter field LOC. We also have the standard deviation under the parameter field scale. And then we also can specify the shape of the array we would like to turn, right? So here I'm specifying a 5x5 array. Note how these are all centered at 0. And if we were to check for variance here, it would have unit variance. Create an array of random integers between 5 and 10 with shape 2x2. All right, the last function we will talk about from the random module, randint, another great one. We specify the starting boundary, the stop boundary, and then the shape. Let's run this a couple times. Can we verify that the upper bound is exclusive and the lower bound is inclusive? I'm pretty convinced. I haven't actually calculated what the probability of not seeing a counterexample would be if I ran this 10 times, but probably pretty low. I didn't see any 11s in there. So upper bound exclusive, lower bound inclusive. That third positional parameter is the shape of the returned array that we would like. And then I guess last note here, randint, again, uniform distribution, like we saw with random.random. Amazing. All right, exercise, creating arrays. Create a 5x5 array of 1s with d type in 16. All right, let's try this. p.1s, and the first parameter is going to be the shape. So we want a 5x5, right? I'm going to pass that shape in a tuple, right? The parameter field expects a single item there, so I'm going to collect it in a tuple. And then d type, this problem is asking me for int 16. Looks good to me. Create an array of 10 numbers drawn from a uniform distribution between 0 and 1. All right, so uniform distribution, what do we think of? We think of the random module and either .random or .randint. So this is saying 10 numbers between 0 and 1. So I'm going to use random.random. And we want 10 numbers. So I think this cuts it, right? We just pass a simple number for the shape field, and we get 10 numbers. Create an array of 10 numbers drawn from a normal distribution centered at 80 with a standard deviation of 5. All right, so this should be random.normal then, easy to remember there. The location is going to be at 80, and the standard deviation, aka the scale parameter, is going to be 5. And then we want shape to be 10. Oh, in this function, the shape parameter is not shape, but size 10. There we go. Notice how I use the tooltip to remind myself of these keywords. As best you can when you're learning Python, it's going to be of value to you to work with the IDE. And not all IDEs are created equal. So find out which IDE you prefer, but as best you can, leverage that IDE that you develop a relationship with, because if you can keep your fingers on the keyboard, if you can keep away from Googling stuff and getting all mousy clicky, you'll become a much quicker developer. All right, create an array of 10 integers drawn from a uniform distribution between 5 and 10 inclusive. So this could be the last module that we learned about in the random module. All right, rand_int will be the one. We want 10 integers drawn from a uniform distribution between 5 and 10 inclusive. So 5 will make the stop 11, right? And we want 10. It's actually, I think we can just use positional parameters here. Note that I just left out the keywords, right? So this positional arguments versus up here, keyword arguments. You can do either one, right? It's worth doing keyword arguments if you're not 100% sure that your memory of the proper positions is correct. So, all right. Numpy array attributes. Common array attributes are shape, size, n bytes, and item size. Well, shape is at least familiar, right? We saw a similar attribute for pandas data frames. Looks like we're going to take a little example here, or a dummy array to go through our examples. All right, so it's just a 5x5 array, having any number between 5 and 9 for an element value. Okay, so let's try and access these attributes. So here's .shape. The number of rows will come first, followed by number of columns. We have .dtype, shows us the data type of every element in the array. We have my_r.size, 25. Well, 5 times 5 is 25. So I'm going to think this is the number of elements in the array. My_r.nbytes. Perhaps we could posit that this is the total number of bytes of the array. And then my_r.item size. Well, to go along with what I said before, 200 divided by 25 is 8. So I think this is making sense, right? So we have 25 items, 25 elements. Each one is 8 bytes. And then we have 200 bytes for the whole object. Awesome. Exercise 3, conditional check on array attributes. Write a conditional that checks that the total number of bytes of the array object my_r divided by the size of each item in bytes is equal to the number of items in the array. Well, I guess this is going along just with what I was saying. We just want to check that condition, right? So my_r.nbytes divided by my_r.item size is equal to double equal sign, right? my_r.size. Excellent. Should evaluate to true. Numpy array slicing, copying, setting. So we've seen slicing in a few different contexts now, lists, as well as data frames. We're going to see them with arrays now. Array slicing operates much the same way as with Python lists. All right, so again, continuing with our dummy data set here. We can grab the first row, right, by indexing at 0 using the square brackets. Square brackets are going to be our, common thread here between lists, dictionaries, data frames, arrays. We're always going to want to use the square brackets. And then the other thing to note is that similar to how when we use df.ilock or df.lock with pandas data frames, we have the ability to grab both a row and a column within one set of square brackets. And in fact, this is going to be the preferred method of accessing a specific element with arrays because it's faster. So let's actually just convince ourselves of this. I'm going to use some cell magic, the time it command, right? And this is going to time how quick it is for me to index my array this way versus having the row and the column appear together in a single set of square brackets, right? So in the former case, it took 236 nanoseconds per loop. In the second case, 122 nanoseconds per loop. So about twice as fast, which makes sense. This is having to index twice. This is indexing once. We can use the same slicing notation as with lists. So I've got start, colon, stop, colon, step. We can do this for any number of dimensional array. So it's just along the first dimension, start, stop, step, second dimension, and then comma, second dimension, start, stop, step, and so forth. So we can do this with however many dimensions we want. Slicing is not an issue. All right, so let's just take an example again with my R. I am going to grab the first two rows and then the first two columns, right? First dimension, second dimension. Slices are views, not copies. This means we can set slices of arrays to new values and the original object will change. Contrast this with data frames, right? If we didn't use .lock or .ilock with a data frame and only use square brackets, we were returning a copy, not a view. But with arrays, we automatically return views, not copies. No need to use something like lock or ilock. And what this means is that you can set the return to new values and your original object will change. All right, so doing the same slice as above, but setting those elements to value of 0. And if we look at the original object, we do indeed have some zeros in the top left corner now. We can also negative slice with arrays. Here I'm grabbing the last two columns, or rows rather, and last two columns. We can also do some cool things with step sizes. So here I'm grabbing every row, right? That's the colon followed by the comma. So the colon is going to say, right? It's the same thing as having the upper and lower bounds at the end of values along that dimension, right? Because we're just not including them. So it's going to grab everything, every row, and then again, implicit start and stop here along the column or second dimension, but we're doing a step size of 2. So we're going to grab every other column. Again, this is going to be a little confusing, but you'll get the hang of it with practice. We can use negative step sizes just like we could with lists. By now, you should have seen it in a couple places. I think you had a lab exercise where you had to reverse a list. Hopefully, you were able to do that with slicing. So here we're going to reverse this array's rows with negative slicing. A negative step size reverses the order of start and stop. So it is a convenient way to reverse the order of one or more dimensions of the array. So here, because I don't have a comma, this is automatically just going to operate on rows. All right, and if we wanted to reverse the columns, we need to do a colon followed by a comma so that we're just moving past that first dimension, not making any changes, and then performing our change along the second dimension. There we see our rows are flipped. Alrighty, sometimes we want to create a copy of an array despite the default slicing behavior. We can do this with a .copy method. I actually didn't learn about this until I've been using Python for quite a while, but this will become very important to you. Python wants to be efficient in memory, okay? So oftentimes, if you are assigning a variable name to a pre-existing variable, you're not actually making something new. You're just creating a pointer so that two different names point to the same thing in memory, all right? So oftentimes, if you're wanting to make a distinct object that's based off of another object you've already declared, you'll have to explicitly say, hey, make a copy of this. So an array is an example of that scenario. So here I'm going to take my old array, my R, and make a copy of it by calling the .copy method. It's a method because we see the parentheses, right? If it were an attribute, there'd be no parentheses. And I'm going to set this to a new variable, new R. And if I change new R so that every element is 0, I will see that my R is unchanged. Cool. Exercise for array setting and slicing. Set all the even columns of my underscore r to 0 and all the odd columns to 1. Interpret the first column to be 1 and the last to be 5. In other words, don't index at 0 when thinking of each column as even and odd. Okay, so if that's confusing at all, it looks like there's an example output here that we can just follow. And let's go. So my underscore r, I want all of the, so every row, right? So no matter what I do, because the rows are identical, I'm going to slice through all rows, right? And that's what I'm doing with the colon comma. And then let's see what this, let's just, iterate over this. Set this to 0 and then look at my r. Yeah, so that's what we want, right? First, middle, and last are 0. So now we want to do the same thing, set to 1, and we want to shift over 1, right? So we're going to make the stop 1 instead of 0. Looks like it's an ace in the hole there. All right, NumPy array reshaping, concatenation, and splitting. Reshaping is going to be a common task for us. We will deal with this a lot with switching between vector and matrix representations before piping something into a machine learning model, for instance. So it's going to be worth our while to get used to the reshape method in NumPy. So I've got this array, one dimension, numbers going from 0 to 9. And let's say I want to reshape it. I call the reshape method and then pass the number of elements I want along each new dimension. So I'm going to have 3 elements along the first dimension, 3 elements along the second dimension. And lo and behold, there we go. We have a 2-dimensional array now. And note the behavior here. We are just counting along the first dimension and then sandwiching on the subsequent elements along the next element in the second dimension, right? So this thing is just reading from left to right from the original array. The reshaped dimensions have to be evenly divisible into the total number of elements. And a side note here, okay, you're going to see me use this later on, -1. If we pass -1 into the shape field of .reshape, this will infer the proper dimension based on the other dimensions provided and the total number of elements. So if there is a whole number division between the original amount of elements and the previous dimensions that you've already defined, -1 will take up that whole number value. This is going to be very useful for us to avoid having to calculate everything explicitly. So let's take an example. I've got np.arrange 12 here, right? 12 is evenly divisible by 4, 3, 6, and 2. So here I'm reshaping into 4, 3. I could also reshape into 6, 2. All right. If I didn't want to, determine for myself that second dimension, I could just put -1. And because my first dimension was 6, -1 will become 2, right? Because it's 6 times 2 is 12. Similarly, I can make the first 4 and the second dimension would be 3. I could make the first dimension 3 and that would be 4, right? You're seeing this. Lastly, if I wanted to reshape into the same number of elements along the first dimension as there were elements in the original object, and I pass -1 as the second dimension, we're going to end up with a 2-dimensional object, but we only have 1 element along the second dimension, right? And that is indicated to us by these square brackets, double square brackets. So this is actually 2 dimensions. Speaking of, a common manipulation in NumPy is to convert a 1-dimensional array into a 2-dimensional array. You will see this frequently when working with test and train data sets in machine learning. Why? Because many of the machine learning APIs that we use may expect a matrix or a vector, right? And if it's expecting a matrix and you pass a vector, you'll throw an error, right? But we can make a pseudo matrix of a vector by just having 1 element along the second dimension, which is exactly what we're doing here in this box, right? We have an original array with 9 elements, and I'm going to reshape it into a 2-dimensional object, but there's just going to be one element along the second dimension. Nice. Okay, so we can also concatenate arrays. So here I've got array 1, array 2. I'm going to print them out, 2 separate things. I can concatenate them by calling np.concatenate and then passing them within some kind of collection, right? So here I'm passing them in as a tuple. I could also pass them in as a list. VStack or vertical stack will place the two arrays on top of each other, right? So here I'm passing them into VStack and they're going to be stacked on top of each other. I could do the same thing with HStack and they are joined side by side, right? Awesome. So here I'm making array 1 is going to be two-dimensional, right? So we see this 3 elements along the first dimension, 2 elements along the second dimension. My array 2 will be one-dimensional with 3 elements. I can vertically stack these two things because that first dimension has the same number of elements, right? 3. So I'm able to vertically stack them. Lastly, we can also split arrays. We give the indices where the split should be performed. So I've got just creating a 10 by 10 array with numbers ranging from 5 and 10 inclusive. And I'm going to split them. So note here that I'm passing my array object into the method numpy.split, and then the index of where I want the split to happen. So if we look at the result, and I'm catching the output of numpy.split into the variables a and b. If we look at where b starts, it's on what was previously index 5 of the original array, right? So this parameter that I've passed to np.split tells where you want the start of the next array to be. Nice. Similarly, we have numpy.vsplit, which will specify a vertical split for an input array. And again, you pass the indices of where you want the next split to start. So 2, 4, 6, 8 in this case. And note, I didn't catch the output here. And so the output is automatically packaged into a collection. It looks like a list of 5 different arrays. And then we also have hsplit. So similar to hstack, vstack, we have hsplit, vsplit. So hsplit will split along the horizontal dimension. All right, exercise 5. Reshaping and concatenating. It's a little bit of a Simon Says problem here. We'll practice a few of these methods we've learned, and we've got an algorithm defined for us. Step 1, make R2 match the shape of R1 using reshape. 2, stack R1 on top of R2 using vstack and call this new array ARR. Step 3, replace all the even columns of ARR with zeros. Step 4, return the sum of ARR using ARR.sum. And it looks like we've got an expected output here to let us know if we got the right answer or not. All right, let's take a whack at it. Step 1, I'm going to copy these steps into my cell down here. Make it a little easier. All right, so let's make R2.reshape. And then we can just pass in R1.shape, right? And it's going to be the same shape now. Stack ARR1, and then we'll want to reset this to ARR2. And because I'm changing, check this out, y'all. Because I'm changing ARR2, actually, in this case, it doesn't matter. If I run this multiple times, we won't get an error because, well, you can always reshape something into its existing shape, right? So this isn't changing ARR2 after the second time. But typically, when you're doing these types of problems, you'll want to copy and paste the original object generating code so that if you run it multiple times, the result is the same. That makes sense? All right, stack ARR1 on top of ARR2 using vstack. So np.vstack, and then I'm going to pass them in as a tuple. We want ARR1 on top, and we'll call this new array ARR. I'm going to go ahead and start showing the output below the cell so we can keep track of our steps. And then replace all the even columns of ARR with zeros. So let's try ARR even. So I'm going to assume that this person, myself, means indexing at 1, right? So this would be column 1 here, column 2, column 3, column 4. So that would be even columns are zeros. We'll see if that computes at the end. Return the sum of ARR using ARR.sum. So now let's do ARR.sum. I get 382. We were expecting 374. Let's try shifting over. I get 363. Oh, yes. Our random number generator needs to be seeded, y'all. Let's try this. Right? So you're seeing firsthand, if we don't seed our random number generator, we end up getting different answers. So now, if I run this cell, even though we're generating random numbers with randint, because we've seeded the generator, it's going to produce the same result every time. Wunderbar. All right, that is it for today. The additional exercises I'll leave for you to solve. If you get stuck, solutions are on the course GitHub. And there is an associated lab for today's session. So after you get done with those additional exercises, go on over to the labs, open up, practice with NumPy, and have yourself some NumPy fun. Thanks for watching.